Hello and welcome to Empowered Learning. This particular video will be about one-to-one functions and understanding the relationship in between a one-to-one function and finding the inverse of a function. So let's go ahead and get started. So the first thing that we want to notice is that if a function is said to be one-to-one, so that is what we'll go on this first blank here. It's said to be one-to-one if each y coordinate of the function corresponds to exactly one x coordinate of the function. Now, what this means is this. For every x value that you have, there is a unique y value that pairs up with it. And because of that type of relationship, if, let's say, we have one x value, let's say it's 1, is paired up with another x value, let's say that's 10, then no other x value can pair up with 10. If we have the situation where we have a function that is indeed a one-to-one function. Every x value is matching up with a unique y value. The difference in that versus a regular function is that a regular function, for every x value that you have, it matches up with a y value. It doesn't necessarily have to be unique. The one thing about a regular function that we have to watch out for is to make sure that we don't have any one x value trying to match up with 2 or more y values at the same time. Okay, so to sort of illustrate what that would look like, we're going to go down here to these examples here. And so we see that we have this first mapping here where we have our domain of 1, 2, 3, 4 for our x values. And then we have our range, pop, dog, pig, and snap. So you see here, this is a one-to-one function because every x value matches up with its own unique y value. Whereas for this particular relation, this relation is a function, but it is not a one-to-one function. Again, so we see here that although 1 is corresponding to pop in the range and 4 in the domain is corresponding to snap in the range, we see that both 2 and 3 are trying to share dog that is in the range. And so here we see that that is not a one-to-one function. The reason as to why this isn't necessarily a one-to-one function is because what a one-to-one function tries to communicate is that you have a function, functional type of relationship going from x to y, as well as going back from y to x. And so we see here that although going from x to y in this case would be a function, meaning that every x value matches up to one y value, going back this way from y to x, we see that in this case, dog would be looked at as our domain, and 2 and 3 would be looked at as the range in that case. And we see dog trying to be with 2 and 3 at the same time, which does not work within a function. Okay, so a one-to-one function just basically means going from from x to y and from y to x. The functional relationship and definition is intact. Okay. All right, so let's go ahead and move on here. So we know that a function is, if it's one-to-one, then of course, then the mapping the values of the domain, the range, and range the domain produce a function. Okay. Now, graphically, if we were doing this, we would do what's called a vertical line test and a horizontal line test. The vertical line test, if you recall, is a test that we do to graphical relations to make sure that they are functions. The horizontal line test is a test to test if going from, let's say, y values to x values in that direction to see if it's a function, if that is indeed a function. And so the vertical line test just basically says, hey, if we draw a vertical line anywhere in our graph and that vertical graph only intersects the graph of whatever we're looking at only once, then we know that it is a function. Horizontal line test does the same thing. If we draw horizontal lines through our graph that we are considering, if we know that the horizontal lines only intersect once, then we know that whatever it is that we're looking at has a one-to-one relationship. The difference in between a graph that is one-to-one versus one that is a one-to-one function is that the graph also has to pass the vertical line test as well. And so I'll show you exactly what I mean here in some of these examples. So for example A, we see that this is a function that is one-to-one because if we draw vertical lines anywhere through there, we will see that the vertical lines only intersect at one point. But also, same thing for horizontal lines, only intersects that particular graph at one point. For B, if you look, we see that this does not pass the vertical line test, okay? So it's not a function. However, and I'm going to erase this right quick, if we were to draw just horizontal lines, we see that the horizontal lines intersect anywhere. Just at one point within the function there. So although this particular graph has a one-to-one relationship, it is not a one-to-one function. Okay. So again, for C, if we draw vertical lines, we see that it is a function, but since that horizontal line crosses the function at 2 points, it is not a one-to-one function. For D, our basic square root function passes both the vertical line test as well as horizontal. So that is a one-to-one function. For E, we have a circle. It doesn't pass the vertical line test, doesn't pass the horizontal line test. So it's not a function and it's not one-to-one. So it's another type of relation. And then any line that we have, if it has a positive slope or negative slope, it will end up passing the vertical and horizontal line test, meaning that it is a one-to-one function. So graphically, this is how we can tell we have one-to-one functions. Okay. So here, if we want to determine if these are one-to-one functions or not, of course, this line here will pass both the vertical and horizontal line test. So this one is a one-to-one function. Here, we know that since this one doesn't pass the vertical line test, then it is not a one-to-one function. It has a one-to-one relationship, but just not a one-to-one function. And for this particular function here, we notice that if we draw vertical lines, of course, there it really doesn't make a difference. But here, we notice that since this is an open circle there, that point doesn't count. And if we draw a vertical line here, that open circle means that point doesn't count. So everywhere where we draw, we see that we have only the vertical line is only intersecting the function once. However, if we have a situation here where we look to see, hey, is this thing going to pass the horizontal line test, we'll see that it doesn't. And the reason why it doesn't is because if we draw a vertical line right along here, we see that every point that's on that particular horizontal line segment is being intersected by the vertical line that we have just drawn, which means it violates the one-to-one function criteria. So we know that this particular stair-step type function is not one-to-one. All right, so now we look at the basic fact. If f of x is a function that is one-to-one with points on its graph of x, y, then we know the following. First of all, any function that is one-to-one has a related function known as the inverse function of f of x. And so how we produce the graph of the inverse function is all we have to do is just interchange the x and y coordinates, okay? So That means that if we have a function f of x that looks like points x, y, then that means here for the inverse, those points are now going to look like y, x. And so the second thing here, let me make sure I get this lined up right. Second thing is that if we have a function and what I like to call its proposed inverse, if they are indeed inverses of each other, then graphically what they are is reflections of each other about the line y equals x. So here is the line y equals x, and we see that if we take our function, in this case the exponential, and we fold it about this particular line here, it will look like this resulting function that we have here that's dotted. And of course, this is also known as the logarithm. So we're going to be studying that in some of the later videos, but the whole idea of a logarithm is just it is the inverse function of an exponential function. And so if we know what the exponential function is, then we also know what the corresponding logarithmic function is. Okay, and so this is a sneak peek into the logarithms, which is here, and the exponentials, which is here, and how they are related to one another. And of course, you see that for the exponential, we have the three key points identified. The point -1, 1 over a, where a is the base of the exponential. We always have the point 0, 1, because anything raised to the 0 power is always 1. And then, of course, we have the point 1a, because anything raised to the 1 power is just itself. And if you notice here, if we go over, you see that this is now flipped, and that's a1. This is flipped, and now 1, 0. And of course, for this one's flipped as well, 1 over a, -1. And so that's how we produce the graph of a logarithm based upon the exponential. Okay. Now, this also works for any type of function that is considered to be one-to-one. All right, so one of the things that we know is that when we have two functions that are what we call inverses of each other, then of course we know that for f, you're going from x to y, and for f inverse, you're going from y to x, as far as the coordinates are concerned. Now, one of the things that we see here is that if we know that the function f and its inverse, f raised to the -1, if these two things are indeed inverses of each other, then do you see how that the domain of the original function is the same thing as the range of the inverse? And vice versa, the domain of the inverse function, and this should actually be that raised to the -1, but the domain of the inverse function is the same thing as the range of the original function. Okay, and so this helps us in being able to find, let's say, the range of our original function here when it's kind of hard to figure out what the range is. What we could possibly do is just look at the domain of the inverse, which would be easier to do, and figure that out. And from there, we know what the domain of the, we know what the range of the original function is. Okay. So here, in essence, this is what we're saying. When we know that functions are one-to-one, the domain of the original is the same as the range of the inverse, and the range of the original is the same as the domain of the inverse. Okay. We also know here that algebraically speaking, if we wanted to show that two functions are indeed inverses of one another without having to graph it, this is how we would do it. We would use it in these composition functions. Okay, and so basically what this does is this mimics the motion that I was talking about earlier of going from x to y and then back from y to x. So wherever you start, once you go to your destination and then come back, you should end up right where you started. And in a layman's term kind of way, that is what these two composition functions, or composition equations, I should say, are talking about. So if we start on the inverse side and move to f and then try to go back the other way, then we should end up right where we start. Okay. And so just to give you an example of what this looks like if we do want to show it algebraically, let's consider the function f of x equals 2x minus 3, and what we're calling this proposed inverse, x plus 3 divided by 2. So here we want to show that these two functions are inverses of one another. So what we have to do is compose one with the others. So we start off by basically stuffing what we're calling f inverse into the function f. So what this means here, I'll go ahead and erase this, make sure that this is clear. So what this means here is that for this one, we're going to take all of this, and wherever we see x, we stuff it in there, or evaluate it at that particular expression. And so you see we do just that right here. These two 2's reduce to 1, and of course we have x plus 3 minus 3, which is just x. So we see that this first part is true, meaning that f of f inverse of x is equal to x. So what that means for us is that no matter what the value is, if we plug it into the inverse function, get a result, and then take that result and plug it into the original function, then we're going to end up right back where we started, which is the value that we plugged in the first place. Okay? So going the other way, now, instead of taking 2x minus 3 and having x plus 3, all that divided by 2 stuffed into there, it's actually going to go in the opposite direction. So now we have this situation, and we are going to basically take 2x plus 3, and we're going to stuff it into x up here. So we're going to take this. Let's try to get this to act right. So we're going to take it and get this to go right here. Okay? And so you see, pull this down some, you see right here we're taking 2x minus 3 and stuffing it in where we saw x. And then from there, of course, we drop parentheses and just simplify, and we see that we get x there. And so now, showing that f inverse of f of x equals x, and that f of f inverse equals x, by showing both of those things, we can now say that both f and f raised to the minus 1 of x are indeed inverses of each other. And so now that we've talked about that, we need to now discuss what it means as far as the process is concerned of finding the inverse for a one-to-one function once we know we have it. And so the process is relatively simple. The first thing that we need to do is, for our function f of x, as we're writing as y equals f of x, we're going to interchange the x and y values. So in other words, everywhere where we see x, we now change to y. Everywhere where we see y or f of x, we just change that to x. Second step is to solve, once we've interchanged the x and y values, to solve for y. Okay? And by solving for y, what we are really solving for is the inverse function. And so then from there, we could either say, hey, this is the inverse function, or use that to be able to find the range of the original function by looking at the domain of the inverse. All right, so let's look at some examples here. So I'm going to go ahead and skip these and go straight here. So what we want to do is find the inverse of these two functions here. And so both of these are 1 to 1. Of course, this is a line with a positive slope, so it looks something like this. So we know it's 1 to 1. So we're going to rewrite this as y equals 4x minus 3, and then interchange the x and y values. And then after that, it's just a matter of solving for y. So we need to add 3 to both sides. And then, of course, after that, we divide both sides by 4. And so what we end up with is a line here, 1/4 x plus 3/4. And that will be what our inverse function is. Okay. So similarly, for the function in B, y equals 2x cubed minus 1, in general, this function looks something like this. So of course it's going to pass that vertical and horizontal line test. So here we just interchange the x and y values. And then we just solve for y. So of course we'll add 1 to both sides. And then from here we will divide both sides by 2. And then the last thing that we will do is take the cube root of both sides. So if we do the cube root of y cubed, we get y, and here just doing the cube root gets us cube root of x plus 1 divided by 2. All that under the radical sign. And so from here we see that our y now is indeed our inverse function. And so that's how we find the inverse function from the original 1 to 1 function. So now for this next example, what we're going to do is find the domain and range of f of x. Okay? And so I'm going to run through this example quickly, and then we'll do another one on our own here. So if you see here, to find the domain of f of x is pretty simple. All we need to do is just look at the zeros of the denominator. And of course, wherever the denominator or what x value makes the denominator equal to 0, we have to exclude that from the domain. And we see in this case that ends up being a 3/2 or 1.5 in decimal form. So since this is a rational function, the only time we have to exclude values of real numbers from the domain is whenever we have vertical asymptotes, okay, or we have removable discontinuities, which we call holes in the graph. And so in this case, the only thing we have, technically speaking here, for our function f of x is a vertical asymptote at x equals 3/2. And so because of that, we just throw out 3/2, and all other real number x values are legal. So now that that's done, we need to come and find out what the range is. Since we know the domain is just all real numbers except for 3/2, then here, if we look back at our original function here, it may not be that easy for us to figure out what the actual range is for. So one of the things that we could do is we could go and look at the domain of the inverse function, and that will give us a clue as to what the range of the original function would be. So here we know that function f of x is 1 to 1. So we know that the range of the original function is the same as the domain of the inverse. So we set out to try to find the inverse. So first thing that we do is interchange the x and y values for our function f of x. Now changing f of x to y and make it easier for us to deal with. So we interchange the x and y values, and then we solve for y. So putting this over 1, we understand we have a proportion here, which allows us to cross multiply. And thus, this is how we end up with this equation here. And so now what we are doing from this point is basically trying to solve for y. So, of course, we distribute here. And then once we distribute, all terms that have y, we put on one side. So this is why from this step here to this one, we are subtracting y from both sides, because we need to subtract y like that. And then, of course, the negative 3x that's right here, since we don't want it on the same side as all the terms that have y, we add 3x to both sides to move it on. And so this is how we get this particular equation here. And then after that, we factor out the y that is in both terms. So now we have y equals 2x minus 1 equals 3x plus 5. And then we just solve for y by dividing both sides by 2x minus 1. And of course, here we look at the zeros of the denominator to be able to find out what the domain of the inverse is. And the domain is all real numbers except for 1/2. So that means the range of the original function is the same thing, which is it is all real number y values except for 1/2. So now we'll go ahead and do this one on our own. So we want to find the domain and range of this particular function. So the first thing I'll do is just say, hey, let this be y. And then for the domain, we know that all we have to do is look at the zeros of the denominator of the original function. So we know that x plus 2 is not allowed to equal 0, which means x cannot be equal to negative 2. Thus, our domain is going to be all real numbers except for negative 2. Okay, so the next thing we need to worry about is the range. In order to find the range of f, we can do that by finding the domain of f inverse. Okay, so to do that, we just need to, as our steps have said, take our function y equals 5x minus 3 divided by x plus 2 and interchange x and y values. So if we do that, so now we have this situation here, and we need to solve this for y. So seeing that I can put x over 1, I now have a proportion where I can cross multiply. So my result is x times y plus 2 equals 5y minus 3. I need to distribute. So this will give me xy plus 2x equals 5x minus 3. Excuse me, that is 5y minus 3. So now from here, we just need to get everything with y on one side, everything else on the other. So we're going to be subtracting 5y, and we will be subtracting 2x on both sides. So in doing that, what we end up with, that's canceled, and we have xy minus 5y equals negative 2x minus 3. And so one other thing that I'm going to do just to make life a little easier for us is I'm going to multiply both sides by a negative 1. And that essentially is going to change the signs of every term here. Okay. So now I'm going to come over here, and I'm going to use commutative property to switch these around. So it's going to be 5y minus xy equals 2x plus 3. We factor out the y. And now to get y by itself, we just divide both sides by 5 minus x. So now that reduces to 1, and we just have y, which is now f inverse of x, which is 2x plus 3 equals 5 minus x. And so finally we see that now if we want to look at the range, all we have to do is look at the domain of the inverse function, which in this case we see that 5 minus x is not allowed to equal 0, so that means x is not allowed to be 5, but we can have everything else. So our range just ends up being all the y values except for 5. And so this concludes the video on one-to-one functions.